Hi, AP Chem students. This is the class video for Tuesday, January 5th, 2021. Couple of reminders here, and the homework is to read textbook pages or watch the videos on the schedule. Take notes. Do FRQs number 5 and 6. Answers are included with these in that big packet of FRQs for kinetics. And then complete the Lab 7 vitamin C clock reaction, calculations and results with your lab group. This is due Thursday at 9 a.m. There was a homework quiz today, and after the quiz, we went over most of section 14.4 on integrated rate laws. We did not get to this practice FRQ during class 2, and we did get to the lab, the vitamin C clock reaction lab. So this is section 14.4 in the textbook, the change of concentration with time. So we're going to go into these integrated rate laws today. Before, we were looking at how rates were affected by changes in concentration. This rate law that I've written right here, rate equals K times the concentration of A times the concentration of B, is called the differential rate law. Now, when we integrate this form, we can get a form of the rate law called the integrated rate law, which relates how concentrations change with time. So there is some calculus that you can do to actually get these into the integrated forms, but that is not what you're required to do, but you're required to be able to use these integrated rate laws. So if we integrate the rate law, we can get this first order integrated rate law. That's gotten by taking this rate law, K, where A is first order, and if we integrate this rate law, we get this form right here. This A naught is the initial concentration of A. A at time t is the concentration at some time, some point in time. This is the rate constant as before. And this is t time. So the first order integrated rate law, if we rearrange that equation, the first order rate law can be written in this form, where this form is the form of a straight line. So I can call this y equals mx plus b. Again, A sub t is the concentration of A after some time t. K is the rate constant. T is time in seconds. A naught is the initial concentration of A. So if we have any three of these quantities, we can find the fourth. This equation has the straight line form again here. So if we plot y here, natural log of A at time t versus time, you can see that time here is x. We will get a straight line if the reaction is first order, and the slope of this line is minus k, so the negative of the rate constant. Just to connect with the equation sheet, you'll see that on the equation sheet, there's a section for kinetics. And it has here, this first one is the 0th integrated rate law. This is the first that we've just looked at. And here is the second integrated rate law. And this is the half-life, which we'll talk about later, for a first order process. Okay, so for a first order reaction or process, T half-life is equal to 0.693 over K. K is the rate constant as before. But these equations, these other rate laws, right, this is not on the equation sheet. Neither is the relationship between the coefficients and the rates. So something like this relationship between products and reactants, or between reactants and reactants, that is not on the equation sheet. Okay, so if these are things that you need to memorize, then you should memorize them. Here are some log rules that probably need to remind you of. I just want to put this in as well. So e to the natural log of x is also equal to x. So if you take a natural log and you take e and raise it to a natural log, you get x back. All right, so we're going to use this first order integrated rate law to try these problems here. This is the decomposition of a certain insecticide in water at 12 degrees C, and it follows first order kinetics with a rate constant of 1.45 years to the minus 1 over years. A quantity of this insecticide is washed into a lake on June 1st, leading to a concentration of 5 times 10 to the minus 7th grams per centimeter cubed. Assume that the average temperature of the lake is 12 degrees C. So part A asks, what is the concentration of the insecticide on June 1st of the following year? So since we know that this is a first order kinetics reaction, we are going to I'm going to write down the first order integrated rate law here. And I'm going to write it as the straight line form. And I know that I need to use this equation because they're talking about time. There's a rate constant here. There's some concentrations, but I don't see rates. So I know that I'm going to be using this first order integrated rate law to relate time to concentrations. So let me figure out my 4 quantities that I need to solve this problem. I need 3 of these quantities, and one of them is going to be my unknown. So the concentration at time t, let's look here. It looks like that's what we're trying to find. It says, what is the concentration on June 1st of the following year? So that's my unknown. Other information, the rate constant is given as 1.45 years to the minus 1. Notice that the units are not seconds to the minus 1 this time. So you always need to look at your units. Next, it says, what's the concentration of the insecticide on June 1st of the following year? So the time is just 1 year. And then A naught, the initial concentration, is 5.0 times 10 to the minus 7 grams per centimeter cubed. So I can now plug these numbers into my equation. So if I take my natural log of A, concentration of A at time t, equals, okay, my minus kt, so k is 1.45 per year, times t is 1 year, so my units here cancel out, plus the natural log of 5.0 times 10 to the minus 7 grams per centimeter cubed. So there's my equation. So you can see that in order to solve for my concentration at time t, I need to get this natural log out of there. So what I will do is take e and I will raise it to that power. I will take this side, also raise it to the power, because I need to do the same thing on both sides. That means that a at time t is equal to e, and when I multiply this out, I get minus 15.96. And once I put that into my calculator, I got an answer of 1.2 times 10 to the minus 7 grams per centimeter cubed. Okay, so there's my concentration after 1 year. In part B, I would suggest you try this yourself by pausing the video and seeing if you get the answer. Part B says, how long will it take for the insecticide concentration to decrease to 3 times 10 to the minus 7 grams per centimeter cubed? So now we're starting at 5.0 times 10 to the minus 7th and going down to 3 times 10 to the minus 7th. So again, here, let me write down my variables. My K is still the same. My time this time, it says how long will it take? So that's my question. My initial concentration is the same. That's still 5.0 times 10 to the minus 7. And my concentration at time t, what we are looking for is 3 times 10 to the minus 7 grams per centimeter cubed. Okay, so again, here we're going to plug into the integrated rate law. So natural log of 3.0 times 10 to the minus 7 equals minus kt. And then times t is my unknown plus the log of my initial concentration. Okay, and then I need to solve for t here. Okay, so I can do some algebra. I need to move this to the other side. That's equal to minus 1.45 t. And then I need to divide by 1.45 on both sides. Okay, and I will get t equal to 0.35 years. So that's the amount of time it takes in order for the concentration to go from 5 times 10 to the minus 7th to 3 times 10 to the minus 7th. Here's another problem. Now again here, look at the units. They are not concentration. This time we are using pressure. Pressure, remember, PV equals nRT is our ideal gas law, and if we get pressure by itself, P equals nRT over V, and N over V is moles per liter, which is concentration. Pressure is directly proportional, so we can use pressure in place of concentration as a measure of concentration. So in this problem, again, it tells us it's a first order process. So we're going to use that integrated rate law again. So, but this time, instead of concentrations, we'll use pressure at time t equals minus kt plus natural log of pressure at initial pressure here. So let's see if I can pick out the things that I need. Oh, it says rate constant of 6.8 times 10 to the minus 4. Okay, what else do we have here? Initial pressure is 135 torr. Pressure after 1420 seconds, that must be my time. And P sub t, should use a time rather than a large t, is my unknown. So again, I'm going to plug into my first order integrated rate law, and I will end up with natural log of pressure at time t equals minus 6.8 times 10 to the minus 4 seconds to the minus 1 times 1420 seconds plus ln of p naught, which is 135 torr, Okay, so again here, if I raise e to that and raise e to this, okay, I can get pt is equal to e to the this quantity here. And once we put that into our calculator and raise e to it, we will get a value of 51 torr for the pressure at time t after 1420 seconds. So how can we actually use this integrated rate law in an experiment? Now this reaction where we convert this compound, basically the carbon and nitrogen are switching places. This reaction, we can take data points, we can measure the pressure of this compound at different points in time, and we can get a nice graph of this line. We can use pressure as concentration again, because as we saw before, pressure is proportional to the concentration. So once we get that line, when we plot the pressure versus time, here we get a curved line. When we plot the natural log of pressure versus time, we are getting a straight line. Therefore, since the natural log of pressure versus time gives a straight line, the process is first order. Okay? If it was not first order, we would be seeing a curved line. Just like in the case of this graph, which is actually for, if it was zero order, we would see a straight line. But we see a straight line for the natural log of pressure versus time. So this process is a first order reaction. And this slope is minus k. So the negative of the rate constant. So if we get the equation of this line, we can determine the slope and use that and obtain the rate constant from the slope. And remember, I will say this over and over, but the order of the reaction of the process can only be determined experimentally. You can only get that from experiment, not from stoichiometry. So going on to the next order, we have second order reactions. And for a second order reaction that has the form like this, where if A is the reactant, has a second order, when we integrate this rate law, we get this second order integrated rate law. So that's the form. And again here, A sub T is the concentration of A at time T. K is the rate constant as before. T is time. And this is the initial concentration. Okay, so I've put this second order integrated rate law as the straight line form. So here's y equals mx plus b. So if we want to obtain a straight line for a second order process, we would plot y here, which is 1 over concentration of A at time t versus time. And the slope of this line would be k. You can see here, this is mx, t is x here, and k would be the slope. So that's our graph, our plot for a second order integrated rate law. So here's a sample problem using this data. The question, here's the reaction, and the question is asking, is this first or second order in NO2? So again, here we need to determine this experimentally using the data. So we'll take a look at these concentrations and we'll plot them. So we're gonna take the data here, take the natural log of each point, as well as take 1 over the concentration. Remember, for a first order reaction, if you plot the natural log versus time, you should get a straight line. For a second order process, you would plot 1 over the concentration versus time to get a straight line. So if we look at these two plots, this is the natural log versus time. This is 1 over the concentration versus time. You can see that this graph right here gives a straight line. It also, notice that the slope of this line is positive rather than negative. And so because of what we have plotted and because of the straight line that results, this is a second order process. Okay, so this is a second order rate law as written here. Okay, and so from this slope, we can get the rate constant. The slope is equal to K. And on a spreadsheet, if you plotted this and then got this got the equation for the straight line, the slope would be K, the rate constant. So I'll show you another example that I did up on Excel for a different problem. So this is a link to that at the bottom of that page with the graphs. And here's a problem from the textbook, and here's a bunch of data. So I've taken the data, I've put in the natural log here as well as 1 over the natural log. And if we plot these out, we can see again that here concentration versus time is not a straight line. The natural log of the concentration versus time is not a straight line, but 1 over the concentration is a straight line. Here's another graph. This is given as a first order reaction. So if we take the pressure, and versus time, if we graph this, right, we can get the slope of this line and then calculate our K. And so this graph right here, we can see that this slope is the rate constant right there. So here's a practice exercise that we skipped in class. But if we read this question over, it says the decomposition of NO2 discussed in sample exercise is second order in NO2 with K equal to 0.543 molarity per second. If the initial concentration of NO2 in a closed vessel is 0.0500 molar, what is the concentration of this reactant after 0.5 hours? So initially you might think, well, what am I supposed to do? You know, what equation should I use to find this concentration? Well, things to notice is that, okay, we've got hours here, that's time. Okay, we've got an initial concentration, so that's some initial concentration of NO2. They also give us the rate constant. So, I've got time. That's a big clue. So whenever you see time, you see initial concentrations, you see something, the concentration at this time, you're going to think integrated rate law. And since this is a second order reaction, we're going to use the second order integrated rate law. So let me write it out here. KT, and I'm going to use the straight line form. So I'm going to go ahead and plug my values in here. So this is going to be NO2 at time t. That is what we're trying to find. So I'll leave that alone. Our rate constant K is 0.543 molarity to the -1, seconds to the -1, times T. My T is right here, 0.5 hours. Okay, so immediately, as I'm writing this, I'm noticing the units, seconds and hours do not match up. So I need to do some uh, converting of units. So I want to convert my hours to seconds, or I could convert my seconds to the -1 to hours, but hours to the -1, but I think I'll just say that there are 3,600 seconds in 1 hour. Okay, so there's my T, and I've converted this to seconds, plus 1 over my initial concentration. There it is, it's 0.0500 molar. Okay, so now I can just multiply these out, and I can figure out what my 1 over A is, what value that is. So when I multiply these things out, I get a value of 997.4. And let me just see how my units come out. Yep, molarity to the -1. And so this is 1 over. I need to take the inverse of this. And when I take the inverse, I'll look at how many sig figs I need. Looks like I need 3. My concentration at T is equal to 1.00 times 10 to the -3 molar. Okay, so now for zero order reactions, the rate is just equal to K, the rate constant. It's constant. It doesn't change with concentration. So we can just integrate this rate law and get this straight line form for the zero order integrated rate law. That's what this is. So as I've said, all of these are available on your equation sheet, but if you want the straight line form, you'll have to do some manipulation. Again, here, A sub T is the concentration of A at time T, and K is the rate constant. T is time, and this is my initial concentration. Okay, so again, here's our straight line form. Y equals mx plus b. And so if we plot my concentration at time t versus time, my x-axis is going to be time. My slope will be equal to minus k. Okay, so there's our slope right there. And so we'll get a straight line if a process is zero order in nature. So then to look at the half-life of these, so what is half-life? So half-life is the time it takes for a concentration of a substance to decrease to half its initial amount, or just amount. And for concentration, we could be looking at amounts rather than concentrations. We could be looking for, particles of a substance, but it's some amount of a substance, and the time it takes to get that substance to go from its initial amount down to half of its initial amount, okay, for it to half what it was before. So for first order, the half-life is the time taken for a knot to reach half a knot. Okay, so we can derive all of these half-life equations from the first order integrated rate law by just putting in half of the initial amount for a at time t. And when you do that, you'll get this half-life equation for the first order rate law, for the first order reaction. So this symbol right here represents the half-life, okay? And the first order half-life is just this quantity right here, 0.693 over K, where K is the rate constant. So you can see that if you have K, you can get the half-life. And if you have the half-life, you can get K for a first order reaction. If it's a second order reaction or a zero order reaction, here are the half-lives. And they do depend on the initial concentrations. So looking at this graph right here, we can see that the initial pressure is 150. Okay, so here's where we start. Half of 150, okay, so down to, here's where it halves. Okay, so goes down by half. Is 75. Okay, so we want to figure out how much time did it take for it to go from 50 down to 75 to this point right here. So if we look down here, you can see here the time is approximately 13,000 seconds to get to that point. Okay, so that's our half-life. Our half-life is 13,000 seconds. Now, from 75 to 37.5, okay, so we're going to go down that much. So we look here to here, and we kind of estimate. This looks like it's about maybe 26,000. So this half-life is 13,000. It is the same as before. What if we went down by half again? So half of 37.5 is 18.75. And so here, if we go down to 18.75, we got to do some extrapolation right here. What do you think this half-life will be based on what you're seeing for these two half-lives? Well, if you're guessing 13,000, you are correct. It's 13,000, 13,000, 13,000. So that is the half-life of CH3NC. What is the order for this reaction based on what we're seeing? It is first order. How do we know that it's first order? Because the half-life is constant. Only the first order half-life is constant. Only first order reactions have a constant half-life. The zero order and second order depend on the initial concentrations. Okay, so those half-lives will vary. Only first order reactions have a constant half-life. And so when you see this constant half-life appearing on a concentration or pressure or whatever, concentration versus time graph, then you know that the process has to be a first order reaction. Okay, so just one more example here. This reaction of C4H9Cl with water that they have shown before, we've seen this graph before, they say that it's a first order reaction. So based on that, we can look at the concentration versus time graph and start off at 0.1 and figure out the half-life that they're asking for in part A. So from 0.1 down to, I would say 0.5 is right here. You can estimate how much time that is. That looks like it's about 350 seconds. So I would say that A is 350 seconds. Part B asks for the rate constant. It says use the half-life from A to calculate the rate constant. So for the first order half-life, we know that it's equal to 0.693 over the rate constant. Okay, so we can use this equation here. T half-life is equal to 0.693 over K. So if we solve for K, K is equal to 0.693 over T1 half. So we can plug in here 0.693 and divide by 350 seconds, and we should get the rate constant for this process. And I'm getting, let's see, how many sig figs here? We should have 2, maybe. The 350 is 2 sig figs. So 2.0 times 10 to the minus 3 seconds to the minus 1. So there's our rate constant. So we skipped a couple of these practice exercises. We may come back to them at some point. This one is, there's answers here. You can do that out and make sure you get those answers. It is in the textbook as well. And we'll go over this rate law summary on Thursday. A little more summary. And then we'll do this practice FRQ on Thursday. And Thursday morning, Scotty, Mr. Nichols, is going to do this Pivot Interactives lab on crystal violet using a absorbance spectrometer. We will be able to use Beer's law to use the absorbance versus time to get a to get data that will allow us to figure out what the reaction order is for crystal violet. So basically, crystal violet is this structure here. It's a deep purple color. And when you add sodium hydroxide to it, it turns colorless because of this bond that is formed right there. So that's the activity on Thursday during class 1. And then today we did a video lab, and I showed this. You should definitely take a look at this link to the iodine clock reaction. It's a great demonstration. And this lab is a environmentally friendly version of this iodine clock. And so here, the reaction that we're interested in finding out about, figuring out the rate law of, is hydrogen peroxide reacting with iodide. And it's been found that this H plus is not is 0 order in this reaction. So that is given to you. So the rate law is of this form right here. And how the reaction works, this reaction, the peroxide and the iodide react to form the I2, the iodine, which is a blue-black color. And we add vitamin C to the reaction to eat up, to consume the iodine that's formed and turn it back into iodide, colorless. So we'll base the rate of this reaction, the initial rate of this reaction, as when this vitamin C is consumed. And at that point, that will represent our initial rate of H2O2, because at that point it will start getting consumed or reacted with the iodine, turning it into iodine, which will keep the solution blue-black. There is also starch indicator that binds with the iodine to create a blue-blackish solution color. I should mention this second step right here is much faster than this slower step. Okay, it can only work if this second step is faster. We can only do that rate estimation. All right, so here, the pre-lab, each person has to do their own pre-lab exercises, but then the lab group works together to collect the data and to complete the calculations and results together. So I just went over some molarity calculations, some dilution calculations, because it's been a while since we've done those. So in order to get the diluted concentration of iodide, we take the initial concentration of iodide times the volume right here. Remember our M1V1 equals M2V2 equation. And we get our new diluted concentration once these three solutions are mixed together. So we calculated that, and then a little exercise to make sure people are okay getting reaction orders. You reproduce a data table from your lab notebook, and then the group works together to collect the data and complete the calculations and results. And that is it for January 5th. And so the next class, we'll start looking at the details of the mechanism and a little bit more about the energy pathways that reactions take. And that will finish out our Unit 5 in kinetics.